Hello everyone, this is Gurtac Yemiscioglu. I would like to give you a brief overview about my research, and I divided this presentation into three parts. My main motivation might be on CMOS techniques, adiabatic logic and logarithmic signal processor, my past research, and my current research, quantum cellular automata. Now, why am I concentrating on beyond CMOS techniques? The relentless miniaturization of integrated circuits over the past 50 years has resulted in ever increasing circuit densities. So, for most of this time, the main motivation for miniaturization has been to increase the computational performance by building faster and a more powerful processors. Now, as Moore's law stated, and this graph is presented over here, the number of transistors in an integrated circuit will roughly double every 18 to 24 months. This means the die size grows by 14% to satisfy Moore's law. Now, as we are shrinking down transistors, we are approaching to atomic levels, which are actually the limits for CMOS devices because we are putting more and more over there. They're smaller and smaller and shrinking size 30% every 2 to 3 years. However, in recent years, these advances have resulted in some undesirable side effects, such as complexity. So, how do you know it will serve the intended purpose? Power density. So, how do you dissipate heat at such small space? And robustness and reliability, soft errors, timing errors, defects, and variations, and circuit unreliability and reduced battery lifetime because of the increased power consumption. And another consequence of technology scaling is leakage power, which is a serious problem. Now, if the continuing trends towards high performance and portable computing and communication devices, it's actually exacerbated these effects, and now minimizing power consumption has become one of the major challenges in the design of electronic systems. And as a result, there is an increasing interest in the application of low power computing techniques at the system, architectural, algorithmic, and circuit level. Now, in the past, this research, adiabatic logic and logarithmic signal processor that I have proposed, I proposed a very large scale integration VLSI design and implementation of a 16-bit clock adiabatic logic processor. Now, this processor is actually implemented both power reduction techniques at algorithmic level, architectural, and circuit levels. Now, figure shows the circuit level, which is an adiabatic logic, which is powered by the power clock, which supplies the power and the clock to the circuitry. This is a typical buffer inverter. It's a dual rail logic, so we have got in and in bar and out bars, and chain of these are shown in the figure as well. So as we are slowly ramping up the power, we are actually slowly charging the capacitors and discharging them without dissipating energy to the ground. And this is a promising approach which we can implement to have a low power circuitries. Now we have used the circuit level and applied to an architecture that is shown over here so that we can easily put a logarithmic processor. So why logarithmic arithmetic? Because multiplication and division in the linear domain is actually going to be performed as addition and subtraction in the log domain. And this is why hybrid logarithmic processors are attractive alternatives. And in order to implement logarithmic processors, efficient algorithms are required to convert a linear number to logarithm and logarithmic number to linear. And in this research, we have used Mitchell, which is one of the most used and easy to implement, to demonstrate the usefulness with the VLSI implementation of adiabatic logic and logarithmic arithmetic. And the architectural wise, most important part is a lin to log converter based on the Mitchell algorithm and log to lin converters and arithmetic unit. And these are just showing the inside of these important blocks: lin to log converter, log to lin, and arithmetic unit. Now, we have fabricated this chip using AMS 0.35 process technology as shown as a microphotograph, and the areas were also important design metrics which we can fit into a compact as much as we can. So in the end, when we try to test this chip, I have designed a board that can be directly connected to an FPGA board and a logic analyzer in order to verify the functionality and the power consumption of the circuitry. So the functionality is demonstrated with some test data where we can feed in the power clock and the auxiliary clocks and feed in 2 by 3 and multiply them out so we can obtain 6, which we have successfully demonstrated. And based on the power measurements, we can easily see that when it's compared with the actual CMOS design and the adiabatic logic simulations and the onboard measurements, the clock adiabatic logic shows energy efficiency, which is increasing linearly up to 89.5 as the frequency increases up to 100 megahertz. And when it is compared to the equivalent CMOS implementation over the entire range of frequencies, we can see the significant power reductions. And these power reduction techniques, when they use together, will have a great impact on the DSP applications because we can actually apply this to more sophisticated algorithms to have more accuracy as a link-to-log conversion. So if I carry on with my current research, QCA is a promising approach because as the electronic scaling, as I mentioned, is approaching to its limits, ultimately arise from the fundamental laws of statistical mechanics and thermodynamics. Now, it is now becoming increasingly urgent to investigate and implement alternative circuit designs, materials, and computing paradigms which can enable the continued exponential growth of computing power. Now, as a result, there's an increasing interest in the application of low power, high density, fast switching speeds, and room temperature operations. And QCA is playing an important role or promising a future solutions. So QCA technology takes the advantage of the quantum effects, which becomes increasingly apparent at scale of few nanometers. And QCA is based upon encoding a binary information in the charge configuration within a quantum dot cell. So these two electrons are charged, polarized, which is a binary 1, and these two electrons are polarized as -1, which is binary 0. And the local interconnection between the cells are provided by the physics of cell-to-cell interaction due to arrangement of electron positions. So as a result of using QCAs, we can create a smaller electronic devices with very high computation switching and low power consumption. And therefore, QCA becomes popular and important to replace CMOS transistors in nanoscale technology fabrication. So if you put a number of cells next to each other, we can actually form a wire for interconnect. If we put cells diagonal 45 degrees to each other, we are forming an inverter. And if you want to implement any logical functions or logic gates, we can use majority gates and fix one of those inputs to either logic 1 or logic 0 and perform any logic gate operations. Now, another important thing in the QCA is clocking. Now, clocking in QCA provides both power and the clock to the circuit. And efficient clocking is implemented using adiabatic clocking, where one clock phase cycle has 4 phases: switch, hold, release, and relax. And I can easily demonstrate these phases using the time steps over here. So the switch is where the cells can be polarized, hold, the polarized of the cells cannot be changed. We are holding the values over there. Release, the cells are depolarized. And in the relax, cells are still depolarized but ready for a next switch. So in time step 0, as you can see across the wire, we have got binary 1. And in over here at the end of the wire, we have got binary 0, which is hold. Now this binary 1 is going to transfer down to these cells over here. Now in time step 0, as these are switching, as this is 1, these are going to change to 1. This is in relax, this is in release, so nothing else over there, and this is in hold. Now, in time step 1, these are released now, so it's not holding it anymore. We are in the release state, which is phase three. Now, this is actually transferring binary one. So this is holding, and these are polarized now. So we are in clock zone one in switch phase. And clock zone two is in relax phase at the moment, and clock zone three is in the release phase. So each clock zone is going into the four phases. Then in time step two, these are released, and this is holding now after the switch, so it can polarize the next cells over here. And these are switching, and these are relaxed, so ready for polarization. Now, when they are ready for polarization, as this was hold, now this is release, and this is hold after switch, and it's actually polarizing the end cells to binary one. So what we are interested about QCAs, there are various research areas in QCA itself, and what we are actually interested in is me and my team, we are currently concentrated on two areas in QCA. One of them is the optimization of five variable functions using majority and AI gates to implement large QCA circuit blocks with reduced area, latency, and depth. And another thing that we are working on is implementation of optimized logic functions for AI accelerators. So what we are going to obtain from the first research or the optimization of the five variable functions, we can apply it to build more complex logic blocks, which are useful for AI accelerators if you want to build something high performance and low power at room temperatures. So I have got two students in my team, Embonemi Godwin and Ahmed Mamdut, currently working in these areas. So that's all I want to say. And if you are interested about our research or if you have any questions, please do not hesitate to contact me. Thank you.